Welcome, guys, to another session on dynamic programming. And today's topic is DPV 6.27. And 6.27 is alignment with gap penalties. The objective here is that the gap functions are nonlinear. Actually, I shouldn't say nonlinear. They're they're a bit more complex, and they are a function. If you have more gaps, contiguous gaps, then the cost function changes considerably. Um, and so that's the objective. Let's look at uh, in a bit more detail what what the problem is. So gap function can be written something like C0 plus C1 times however many gaps there are. So C0 can be seen as a gap opening penalty, and C1 is seen as like a gap extension. And if you have k gaps, then you have C0 plus C1 times k. So that is the difference here. Otherwise, the problem is very similar to the last time. There's a scoring matrix that gives you, if you compare any character with any other character in the alphabet, what the penalty is, and assume that a gap versus a gap is zero, and so on. Now, sometimes you will see this terminology indel being used. That is when you open a gap, you either inserting a gap or deleting a character. So it's sometimes referred to as indel. But why is this problem important? Because the book describes this as for DNA sequences, nature tends to insert groups, and so assigning that insert groups of these characters inside gene sequences or DNA sequences, and so it's you would get a much lower rank or score of to DNA sequences if you don't account for this. And all this is saying this gives you a much better score because the cost of having, some contiguous number of differences is much lower. The penalty is much lower because the more contiguous the sequences are, the penalty is not the same as k times some gap penalty, right? So with that, let's look at how to solve this problem. It's also known as affine gap problem, and I've left a link here because this problem has been. I took the help of this gaps.pdf file to describe or build up my slide deck here, and also to understand how the problem is solved, because this PDF helped me to understand what was the flaw in my thinking trying to solve this, because I applied the same approach as the previous solution, which is, you just take, if you want to solve for this box, you look at the best solution here, the best solution here, the best solution here, and then you apply the simple equations. This would be the difference, this would be a gap here, and this would be a gap here, and then you compute the best. If you read this PDF, it describes that this is not the best solution. But, it took me a while to understand why that is not the case. So I'm going to describe to you why I think that, the simplistic approach of what we did in the previous solution does not work here. And the reason is the following. In this case, first of all, in this case, you have to keep three different values, three different matrices, if you will, because you have to remember what the best way to arrive at any box is, either by matches or by skipping on this dimension or skipping on this dimension, and you have to keep all of them. And I'll just give you a quick example of why that is important. So now let's say that you're going from this box to this box, right? When you try to compute this box, you'll try to come at it from this point, from this point, and this point. So what happens is that, let's just take this. You're going in this direction, right? You're moving from your left side to the right side, and you want to compute this box. Now, what happens in the previous example was that we just took the best value, and that best value was stored as m. And what happens is that in this case, the penalty is different if you come from the M solution versus if you come from X or Y solution, because we are aware of how many gaps were opened before. So when you go from left to this point, if you're coming from M, you're going to open a gap and add a gap. So you're going to add minus C0 and minus C1 both. But if you come from X, X again was going in this direction. So when you go in Y direction, again you open a new C0 and C1 when you go in this direction. But when you come from the Y direction, when you had some value here and you want to move this direction, you're just extending the Y, so you only incur the C1. So if whatever was the best here, let's say M was the best, right? It was the highest. If you add the same value to all of them, M would still remain the highest. So the you can forget about the others, right? It's not relevant. But what happens in this case is that because you're adding different values to this, whatever was best here does not remain the best. So you have to compute from all these three. And that is the key to understanding this problem, is that you have to keep all the three, even though M may have been in this case X is the best, but it's not guaranteed, because when you add different numbers, when you go in this direction, normally it's just a gap, but in this case it's a gap here, it's a gap here, but oh, I'm sorry, it's a gap here and here, but it's not a gap here because it's just an extension in this direction. So that was the intuition behind knowing that this problem cannot be solved by the conventional solution that we tried last time, which just knows what the best way was. In this case, you not only have to know the best for a given box, but you have to remember all the solutions. You have to remember if you came by matching what the solution was, if you came by extending on the y-axis or the x-axis, you have to remember all these three solutions. And for any given box, the answer is really the best of these three, right? So for any given box, the answer is the best of these three. But when you derive these values from the previous boxes, you have to remember all three values. You cannot skip any value because what you add to them is not the same, right? And so that is the intuition here. Now keep in mind that if you go in this direction, it actually still works. You can choose to just keep the best value here, because you are adding the same value. When you go in this direction, you're adding delta ij, which is delta ij is the scoring matrix value of C and T. When you compare C and T, you're going to add to all these three, right? Which is what the equation is here. We'll check that out in a second. But when you come from this direction, it still works because you're adding the same cost scoring delta ij to all these three. So whatever was the best, if you add the same value to all of them, the best will remain the best. It's not going to change. So coming from this direction, the best can be used because the best will remain the best. However, the recursion is defined in a certain way. You can read this paper here, but the recursion is defined in this way, and I'm fine with that. I think this works as well. But I think the improvement on this would be that if you knew only the best, you could simplify this and not compare all of them. But in this case, we'll just follow along with this. And so the fact that we understand the importance of the three matrices M, X, and Y is the most crucial part of the affine gap problem. And if you understand that, if you have not understood this, I would say go back and listen to this section again. Once you understand this, then only move forward, because this is the most critical part of this solution. Because it took me a while. I kept thinking that I would just remember the best solution in any box and remember which direction it came from. Either it came from here, here, or here, and I could either extend the gap or I could just keep moving, right? So, but the point is that the best solution is not always continuing to be the best solution, because the cost functions keep varying. You have these three solutions, let's say any one of them is the best, but when you go in this direction, the cost function adder in these cases is different. And so whatever was best may not remain the best going forward. And that is crucial. So now that we got that out of the way, the next thing is you have these matrices and Recursion values are defined here. Um, there is a little bit tricky part to initialize these. So the first thing to understand is that the initialization for this dash dash, which is the beginning, m we used to put as 0, and we'll still put that as 0. The difference is that the starting point for x and y is, because these are gap functions, and our gap, if you go look back, our gap is defined as c0 plus c1 times k. The convention here is that you would start off this x and y on the very first in the gap versus gap as minus c0, which is, you have opened a gap penalty and you put that here. Now I'll also show you, if you go down in this direction and this direction, these are still initializations and boundary conditions. So what you will do is, in this y direction, as you move across y, you can apply this matrix here. And what you will see is that this was C0, and the best here would be C0 minus C1. And then if you keep applying, this is just an extension of gap, and the gap keeps extending in this direction, and it'll be minus 2C1, and this should actually be minus 3C1. This is incorrect. Um, so it'll just keep going in this direction. The cost was opened here, and the gap cost keeps extending this in this y direction. Now in the x direction, same thing happens. If you follow, this was minus c0, this will become minus c0 minus c1, and then minus c0 minus 2c1, and so on and so forth. I apologize for that mistake here. So, and then what is the remaining values? So the remaining values you simply fill as minus infinity. Okay, whatever this on the y-axis, the only value was this y. Y was filled up. Once you filled up, all these remaining values you fill with minus infinity, and on this dimension also you do the same. You fill it with minus infinity. Okay, so that is one way I was thinking about this minus infinity, is that, the m values are derived from the values above, the x values are derived from the values above, the y values here are derived from values on the left. So none of those exist. So conventionally it's easy to remember, set those values which you have no reference to, set those as minus infinity. So now once this is done, once you have filled this first column in the first row, then you can start to apply these recursion equations. And the recursion equations are that you have this match, mij, the xij, which is flowing in the I dimension, which is in this direction. This is the x dimension, and then this is the y dimension. Okay, so not to be confused with x and y axes, but these matrices are written. This is your y dimension. This is your x dimension. Okay. So now what do these recursions mean? Let's just look at that for a second. So they're pretty straightforward to understand. Um, the value here, when you look at the M matrix is just defined in this diagonal dimension, because it always requires a match between these two characters, T and C. You're not introducing a gap, so you must take both of these characters, and now you must pay the price for whatever. Either they are the same, in which case you got a match, or they're different, you have to pay the price for that. So this direction, the match matrix, means that you're choosing this path of going diagonally. And so this delta ij is, and that's why I was saying, because this is applied to all these three, whatever was the max or the best here would remain the best even as you add this, because it'll remain the best, right? You're not adding different values to these three. So that was my intuition there. Now, this is basically just derived from this diagonal here. You take the best here and you add a cost and you get this m value here. Okay. Now the xij, which is going in this dimension. Now if you go in this dimension, what you have to do is you take all the, if you go above, you take the previous and you take all these three values. Now you have to see this equation has different penalties. So for the match, if you had a match here and you're opening a gap, if you go down this direction and you're opening a gap, then you have to add a full C0, C1 penalty. Okay, because you have to open a gap in that. But if you were in the x dimension, if you take the x part of this matrix, then there was already a gap, right? Because the x already in this dimension, if you move along this dimension, x was already open. So if you happen to pick from there, you just have to extend it. And if you happen to be picking from a y, one of the y matrices, then y was moving in this direction. So if you change direction and if you start going in this direction, you have to still pay the full price. And C0 and C1, you have to pay the full price here. So that's how xij is computed. Yij is very similar, but in the other dimension. In that case, you're coming from, again, when you go compute this y, it can come from any of these three. If you come from m, you have to pay the full price. If you come from x, um, x was going in this direction, so x also has to pay the full price. Okay, but if you come from y is already open. That page is already open. That gap penalty is already open. So you just have to pay an extension penalty in this direction. And that's what you see here. When you come from y, you pay extension penalty. When you come from m and x, you pay the full penalty. And that is the secret of these equations. Just remember, go through these equations and understand what match is. Match comes this way. Gaps and extensions go this way and this way. When you move along this, you're inserting the indels or your insertion deletion operations. Try to skip a character or try to introduce a gap, whatever you want to call it. But those insertions, deletions, etc., when you move along these horizontal and vertical dimensions, are described by these equations. And when you go across this diagonal dimension, that is this equation, the match equation. Okay, so so very quickly, let's just look at this match. So when I want to compute this match, I'm going to come from here. I'm going to look at all these three. I'm going to pick the best, and then I'm going to add the delta TC, delta TC right here into this, and that would give me the m value. And then I would compute the x values coming in. The x values come from this dimension, and then the y values come from this dimension. So and you have to take all these three and boil them down to this y value here. So that would be this. Once again, I'd like to give credit to this website and this lecture on bioinformatics, and that gave me the direction for the solution. And so once you solve for this box, basically just keep applying this all the way through. And when you get to the very last one, the answer would be sitting right there. And you say, what is the answer? I've got three values. So the best value of the three values in this box here would be the answer. And that is how you get the best score with this affine gap problem with C0 plus C1K. And what is the order of the solution? The order of the solution, again, we did constant number of operations at each step. We didn't go check every possible value in this direction or that direction. We just used the previous, but we used three computations to get to this one. And three here, and three here. Um, so to fully compute this value, we actually looked at 9 different computations. Okay, but still it's constant time. It's 9 times mn, which is the same as mn. And so the order of computation here for this affine gap problem remains order mn. So that's it for this episode, guys. Thanks for watching, and hopefully you enjoyed the solution. And if you did, give me a thumbs up or subscribe to my channel. As usual, if you like dynamic programming solutions, are interested in looking at these kinds of problems, then do come back to my channel. Or you can leave me comments about if there's any specific problem that you're looking at and would like me to also present here. I can do that, assuming that I find enough time to be looking at these problems. Sometimes these problems are simple, but like this problem was quite a bit involved, and it took me some time to digest this solution. And eventually, I think after enough racking my brain, I did understand how this the underpinning of this solution was why did the previous solution not work and why did we need these three matrices, and that was the key here, the intuition there. Once I got that these equations, look at these equations, they don't have constant additions, they have variable additions. So the best in the previous stage does not remain the best if I keep changing what I add to each step. And that once you get that, then I think this whole thing falls into place. And once again, thanks for watching, guys, and I'll see you in another episode. Until then, take care and bye bye.